So Taguchi used a signal-to-noise ratio originally from the average quality loss to become the quality index. So in order to estimate the signal-to-noise ratio, we need to do some samples. Therefore, we can get the average output and also the standard deviation. But how to do the experiments become the topics we would like to discuss today. And design of experiment is an application of statistical techniques. And the purpose of design of experiment is try to make a small number of experiments, and for those experiments, they are efficiently designed in such a way we can get a good estimation of the distribution parameters. And also we can use this method to study the effect of all the parameters at one time, rather than one factor at a time in the conventional method. So the advantage of using this statistical design of experiment is we can use less experimental cycles, and also we can shorter the experimental period and also lower cost, and we can get a satisfactory result in an efficient way. Design of experiment is not a new thing. It's first proposed back in 1920s by a Britain geneticist, Mr. Fisher. He applied the DOE into agricultural productions, and he tried to come up the best combination of the distance between crop and also how much fertilizer you should put, and what's the best pruning time. And he used statistically based experimental methods and get the best combination for the highest crop, the production of crops. And in 1930s to 40s, a design of experiment was introduced to industry productions in America and Britain, and it become getting more and more attentions. But when it come to 1949, DOE was led into Japan, and by Japanese experts, which is Taguchi, he developed out, he come up a term called orthogonal array and simplify the methods. And he applied this method in industries for 10 years and got the great economic benefits and also raised a lot of attentions. And in 1957, Taguchi he invented a concept of signal-to-noise ratio, just what I just introduced in the last sections, and using the analysis of mean to get the robust design. And he called this method to be Taguchi method. 7 variables. And how do we do? We usually use try and error. So we fix 6 factors, for example, B, C, D, E, F, G, and only change factor A, and try to see what value of A will give us the best output. And after we get the best output for certain value of A, we leave A here, stay here, and fix the rest of the value C to G, but only manipulate factor B. Again, try to see what kind of value of factor B will give us the best output. And we do this continuously for factor C, D, E, F, G. And at the end of these iterations, we might get a kind of combination where the output is the best. But we should do this iteratively, which means that we can do that iteratively, which means we can come back to adjust factor A again and make the rest of the factors fix at the values we just found. And again, to A to G, we can continue to try and error in an iterative way and to see, soon, fortunately or finally, we can get the best output. But as I just explained, this method is very slow, and this kind of loop experiments may not converge. So So Fisher's experiment, DOE, is based on factorial experiments. What is factorial experiments? Assume we have two kinds of factors. One is continuous factors, such as the length, the weight, the speed. And the second type of factor is called discrete factors, which is also called category variables or attributes. For example, we have three different selection of machine 1, machine 2, machine 3, or type of gasoline. We have 92, 95, and 98. They are not continuous. So in the discrete variables, we only have finite choice. We can just either choose A or B or C for certain variables. But in the continuous factors, they usually have a range. And within this range, there are infinite choice of factor values. And so, in factorial experiments, we try to reduce these selections for continuous factors. They only assign finite level, finite setting, finite possible settings for a certain continuous factors. Why do they want to do so? Because they want to reduce the searching space for continuous factors. And so we need to determine the searching range, and then within the range, we select only finite settings for these factors. But when we consider range, we need to balance between a small range and a large range, because if we only search for a small range of factors, we might miss a lot of useful information, and also we might just searching locally rather than globally for our design. But if we define a big searching range, then there might be some infeasible design coming out, or the system may become highly nonlinear, which will be make our selection of optimum become very difficult. In order to reduce the searching space, we would like to convert all the variables into factorial variables. Say for discrete factors, it's easy since we only have finite choice for discrete factor. But if it is a continuous factors, we could have infinite possible selections within the range. So we can convert that into a factorial variables in such a way these variables will only have finite possible settings within a range. And the factorial level is the number of possible selections. So in this way, all the variables will have possible selections only. So in total, the possible combination will become finite as well. So in this case, we can reduce the searching space. So how to determine when to use the labels of the variables? When to use 2-level factors? When to use 3-level factors? Say here, factor A is a 2-level factor because here we only have 2 possible selections, A1 or A2 for factor A. And factor B is a 3-level factor because they have 3 possible settings for factor B. And we would suggest to use 2-level factor if your system is linear or monotonic. Why? As you can see from here, this system, the output response is affected by factor A. But the relationship between the A and output is a monotonic way, which means that when A increases, the output Y will increase in one direction. Therefore, the optimum, if we are looking for the maximum will occur either at the upper bound of A or the lower bound of A. So we only need to search 2 positions. We can determine the value of A for the maximum output. So we suggest a 2-level factor if you know the system is linear or monotonic. But if you don't know if this is a linear or monotonic system, or you already know it is a nonlinear system, then we might need to go to 3-level factors. For instance, like here, this is a nonlinear system. And if we are using 3-level, we can get that at the level B2, the output will be the highest. Even though in the real system, the maximum output might occur not right at B2, but here, but they are not that far away. So in engineering optimization, the selection at B2 is good enough. And we are searching for to solve the problem in a quick and efficient way in engineering applications. And we don't really care the minor increase for the output, the minor increase, because we want to reduce the searching time and reduce the number of experiments. So after we assign the levels for each factor, now we confine the searching space to the finite number of combinations. For example, we have A control factors, and each factors are set at level B levels. Therefore, in total, we will have B to the power of A number of combinations. For instance, if we have 3 variables, 1, 2, and 3 different variables, and each variables we assume to be 2-level. So in total, for these 3 variables, variable 1 has 2 possible selections, variable 2 has also 2 possible selections, 3 has 2 possible selections. So in total, there will be 2 by 2 by 2, 8 possible selections. And we call this, if we are consider all the possible combination for these factorial experiments, we call this a full factorial experiments. So in this case, we can look at here the possible combination for 3 factors A, B, C. Each factor has 2 levels. There will be in total 2 to the power of 3, 8 possible combinations. We call this treatment 8 possible combination or 8 treatments. And if we assume 3 levels for each variables, and if we have 2 variables, variable A and variable B, like here. So variable A has 3 levels, 3 possible selections. Factor B also have 3 possible selections. So there will be in total 9 possible selections for these 2 factor problems, and each factor has 3 possible levels. And this is a full factorial for 3-level factors. If we have 3 factors, factors A, factors B, and factor C, they are all 3-level factors. And the total number of treatment, or the total number of combination for this full factorial, there will be 3 to the power of 3, in total 27 possible combinations. Here we can use this dot to represent the possible treatment, and this is factor A, factor B, and factor C. Factor A, there are 3 possible selection. Factor B, 3 possible selection. Factor C, also 3 level. So as you can see, there were in total 27 possible combinations for these 3 factors. And so the full factorial for 3 level factors, there will be in total 27 combinations. So if we have 3 variables, and each variable has 2 levels, so in total there will be 8 possible combinations. Let's use this one as an example. An experiment is conducted to determine the effects of 3 factors, and the 3 factors are holding pressure, booster pressure, and screw speed, which is the variables in the injection molding process. And we want to determine what is the best combination of these 3 factors in order to reduce the shrinkage in the injection molding process. Say here, for each factors, we have 2 possible selections because this is 2-level design. So we use the sign -1 to stand for the first choice, first level, and 1 to stand for the level 2 for this factor A. The same thing for factor B and factor C. -1 stand for level 1 and 1 stand for level 2. So we will have in total 8 possible combination. For the first experiment, or we call it treatment, factor A is set at level 1. Factor B is set at level 1, and the same for factor C. And these are the experiments. And the experiments is based on the repeated samples. So we have 2 samples based on this combination of parameter values. And 21.9, 20.3. Same thing for treatment number 8. All the factors are set at level 2, and these are the output of this treatment. And this is called the full factorial 3 variables experimental design. So in total, 8 numbers. We can analyze the influence of each control factors on output using response table. What is a response table? Assume this is an experiment. We just introduced the full factorial experiment. We have 3 factors, and each factor has 2 levels. And we have 2 samples for each treatment. And we can get the average output for these 2 samples. And so this is the average output for each treatment. And in the most intuitive way to get what is the average output when factor A is set at level 1. Here we can determine which experiment this one, that, this, and that. The factor A is set at level 1. So we get the average output of these experiments 1, 3, 5, and 7, and this is the average output when the factor A is set at level 1. We can do the same thing for level A2. And here we come up that the experiment number 2, 4, 6, and 8. This experiment, factor A is set at level 2. So the average output when A is set at level 2 can be obtained using this equation. Similarly, we can get the average output for factor B1, B2, and also for factor C at C1 and C2. And we can put all the average output over here, and this is called response table. For each variable A, B, C, the average output when A is set at level 1 will be 21.65. Same thing for factor B. At level B1, the average output will be 17. As you can see from here, we can use the average of these 2 levels to double check if we have any miscalculation, because all these are average of the 4 experiments, and these are average of the other 4 experiments. So in total, the average of these 2 will be the total average of all 8 experiments. Similarly, here B1, there are 4 experiments, B2 are the other 4 experiments, and the average of B1 and B2 will be the average of the all 8 experiments, which is supposed to be the same as value A. So here they should be the same. So we can use, I often use the average of the level to double check if there's a miscalculation. We can show the response table in a graphical way. We call this effect plot. Here, factor A, B, C, and we can plot the response table values over here, A1, A2, same thing for B1, B2, C1, and C2. We call this effect plot. And we can come up the effect plot using Excel, where we will do this practice in class. And here, when you look at the effect plot, it's very easy to determine the best combination of the parameters. Since in this example, we are looking for the minimization of the shrinkage in an injection molding part. Because level A2, when factor A is set at level 2, which is A2, the average shrinkage is smaller. So if you want to pick a level for A, it seems A2 is the better choice. The same thing for factor B. When B is set at B1, the average shrinkage is smaller when B is set at B2. Same thing, C1 seems a better choice. Therefore, by looking at the effect plot, we can conclude the combination of A2, B1, and C1 will give us the smallest or the minimized shrinkage in the injection molding design. So let's use this Canon Canon example to demonstrate the efficiency of using full factorial design. Say you are shooting a cannon and you have two variables you can adjust. One is the angle, elevation angle. The second one is the propelling force of the dynamite, which means how much dynamite you should use in a cannon. And the weight of the pellet is m, and the gravity, it would be 9.8. And the range, the possible range for the elevation angle is between 0 to 90 degrees. And the propelling force you can select for the dynamite is between 0 to 70 Newton. And here we certainly won't be able to shoot a cannon in class, so we use a theoretical formula to represent the selection and the shooting distance based on the selection of angle and a propelling force of dynamite. So once we get F, the propelling force, and also the angle, we can use this formula to estimate the shooting distance, and using this formula to assume this is the experiments. So first, we want to convert this Canon example into a factorial experiments. So for the propelling force of dynamite, within the range, we assume the range to be between 5 to 15. And the elevation angle will be assumed to be between angle 20 to angle 80 degrees. And here we are using 3 levels for each factor, since we are not sure whether this system is a linear system or a monotonic system or a nonlinear system. So we play safe. We first assume each factor to be 3 levels. So factor F1 to be 5, F2 10, F3 will be 15. And alpha, there are 3 possible selections, 20 degree, 50 degree, and 80 degree. So therefore, in total, there are 9 possible combinations, which means that in this full factorial experiments, there are 9 possible treatments. So here, we can set the force to be 5 Newton and set the angle to be 20 and shoot the cannon to see what is the distance. And here we are using the theoretical formula to get the distance. And this is the value we have. So now we want to determine what kind of combination of F and alpha will give us the longest shooting distance. So assume we don't know we don't have any theoretical background and how to get the best combination from the selections from the full factorial experiments. In this case, it will be easy because we assume each factors to be factorial variables. So there are only 3 possible settings, so there are in total 9 possible combinations. So the best design will be the best within these 9 possible choice. So in this case, experiment number 8 is the best combination because when F is set at 50 Newton and the angle of alpha to be 50 degree, the shooting distance is the longest, which is 565 meters. But we can also get a similar result using the response table or the effect plot. So we can try that in class and to see if we can come up the response table for this kind of example. And this is the value I have for factor F and factor alpha. And we can using a graphic method to illustrate the response table, which is called effect plot. And this is the corresponding effect plot for this kind of example. So by looking at this effect plot, we can understand the inference between the propelling force to the shooting distance. So when F increase, the propelling distance increase. And this is very reasonable. It is consistent with our understanding. And for the angle alpha, as you can see, this is a nonlinear case. Alpha will have a better choice. When alpha is set at alpha 2, the shooting distance is the longest. So if we are looking for the longest, the possible, we are searching for the combination of variables in order to get the longest shooting distance. It's better to use F3 and alpha 2, right? Because from this effect plot, if this effect plot represents the inference of the variables on the output, then F3 and alpha 2 seems the best choice to have the longest shooting distance. And we can compare this selection in the experimental design, in the full factorial design over there. Because in the full factorial, we know that experiment number 8 will give us the longest shooting distance, and which happen to be F3, level 3, and alpha 2, level 2. So is it only a coincidence, or we can determine the best combination in the factorial by simply use the effect plot? This is something interesting, and we will continue the discussion later.